Can you see my notes here?
Yes, yes.
Okay. Okay. So so PCA, principal component analysis, is a dimension reductionality process. Okay. What is dimension reductionality? Okay, dimension reduction means, see, dimensions are your features, right? Because each feature is like one dimension in your program, right? In your machine learning algorithm. And higher the number of dimension, more complex it becomes, isn't it? Okay. So, so imagine, like, if you talk about SVM itself, now when you have just two dimensions, you can easily imagine a line. But if you take three dimensions, okay, then it becomes a plane, right? In three dimension, you have to have a plane, and then you keep increasing, like 4 or 5 or 10 dimensions, right? It becomes even more difficult. Okay, and of course, it's going to take time. Okay, it's going to take time. It's going to take um, more um, effort, in the sense that, when you start prediction will also take time. But at the same time, okay, we ask ourselves this question: are all these dimensions that we are giving, are they equally important? Okay, so dimension reductionality is a process of reducing dimensions. Okay, but at the same time, we are reducing, or we are removing dimensions which are, I mean, everything will affect. It's not like they are not going to impact. Okay, but their contribution is very less, almost negligible, right? Now, if its contribution is negligible, then why do you even keep it? That's the question. Okay, so PCA is one. There are many. Okay, there are many such algorithm, but one of them is PCA. Okay, and we are our objective here is to see which dimensions or which features is contributing what percentage to the accuracy, or to the final accuracy, that final prediction that model is going to make. Okay, so based on the percentage, okay, we decide whether we should include it or not. Okay, so if let's say you take uh, three features, right? And first one, Princia will tell you the first one is contributing 80% to it. Second one is contributing 19% to it. Third one is contributing 1% to it. So you can get those, data using your PCA analysis. Okay.
Yes.
So um, um, it uses what is called as, okay, singular value decomposition. Okay, singular value decomposition, the process using which it takes each metric, and it will tell you the contribution, okay, or how much it is contributing to the final analysis. So we'll take one example here, okay, and I will understand the theory aspect of PCA. Okay, so then we'll come back and we'll do a program. So let's see how it actually works. Okay, what does it do? How does it calculate? Which is important. Now you see here, okay, let's say we have a data set with simple 6 rows. Okay, we have 6 rows data set, and it has 2 columns, maths and science, and these are the marks. Now, if we measure only one subject, we can plot the data, okay, like this. Okay, so you're plotting this data here. So your first value is 10 and 6. So maths 10 and science, sorry, maths 10 and science 6, correct. So maths 10 and science 6. Then 2 is 11 and 4. Okay, so science 6 is the highest, right? That's why you see here. So when you plot this, okay, you get a graph like this, right? Okay,
Yes.
so this is the data set. Okay, now we want to see which one is contributing how much, science versus math subject. Okay, so first thing it will do is plot this graph. Okay, and okay, so since we have only two graph, it is two dimension, right? And it will be easy to understand this. And once you understand this process, you can extend it to three dimensions as well. Okay, 3, 4 dimensions. Okay, so this is just step one. Now, step two is calculate the average measurement for maths, okay, on x-axis and y on, because why we have on y-axis, right? So you do that. And reason we are doing it is we are trying to transform it, okay, we are trying to transform it to a point, okay, so that, okay, the values are, this value average coincides with origin. Okay, so in the next page you will see, okay, so we are taking average of all the values. So these are all the values of science and these are all the values of maths. If you take average, you will get somewhere here. Now this one you move to origin, so that average becomes 0 basically. Okay, now see, average becoming 0, but these points are not changing. The relationship between these points are same. We are maintaining the relationship. So when you imagine, like, the points are slowly moving towards origin, so you end up getting something like this. The relationship between these values, okay, this is very similar to what we do in min max scaling. Okay, so your points remains as it is. Okay, so your center of this data set is aligned to the origin, 0, 0. Okay. Now PCA will start finding the best fit line. Okay. So this best fit line, okay, okay, will start going through this origin. Okay. So let's see. I think I have it here below. Okay. So see, yeah. Okay, now when you draw a random line, okay, which passes through origin, you calculate the distance, okay, between the point and this line. Okay, each of this point and this line. Okay, and so again, just like what we discussed in regression, it draws infinite line, right? And it ultimately you will find a best fit line. So ultimately this one looks like your best fit line, correct? So this passes through 4 and 5, so distance is almost 0. Here also distance is least. Okay, so you find, okay, so this is your best fit line here. Right? Now what happens? Now to quantify how good this line fits the data, PCA projects the data onto it, and then it can either measure the distance from the data to the line and try to find that line that minimizes those distances. Now you see, how, how do I know which line is best? Okay. See, whatever be the line, wherever see, here it's anyways passing through origin. So the slope is what is changing here, right? Slope of each line is changing. The distance between each of these points and origin, will it change when you draw a line? No, right? Origin is also fixed and this data set is also
Yes.
fixed. So this line is not going to change. Okay, so let me take you to Paint and try to show you what actually happens, how PCA is finding the best fit line. So let's say you have a line like this. You have, okay, so this is origin, okay? Now this is your origin. This is your origin, and let's say this is your point. Okay. Now, if I draw a line, okay, I'll take different colors. If I draw a line, green line, let's say. So I will draw a rectangle, right angle triangle from here till here. Okay, so this will be, to find a distance between line and a point, you have to draw a perpendicular line, correct? Let's say this is perpendicular line. Okay, so now you draw. Okay, so this, right? Now, this is fixed, correct? Okay, now this is like your hypotenuse, correct? The fixed line which is fixed, this is like hypotenuse. Now, that's the distance between 2 points, origin and the given point. Now, if I draw another line, let's say, okay, I'll draw another line like this. Now, again, I'll find something like this here. And you draw hypotenuse, which will be green. The orange and green will fall on each other because that's the distance between this. So how do you write this equation? You write, so this, let's say if this is A and this is B and this is C. So we say A square plus B square equal to C square,
Yes.
right?
Yes.
Now, let's say this is green. AG, BG, now equal to C is anyway same. C will not change. We are not changing origin and the point. So
Yes.
this hypotenuse is going to be same. So AG square plus BG square equal to C square. Now here you will have AO, A orange square plus B orange square is going to be C square. Now if C is same, right? And when you have this orange value getting decreased, right?
Mhm.
That's why we say best fit line. So
Mhm.
when you have this best fit line decreasing, what happens to A? See, A is
Decrease.
increasing, right? A has to
Yes.
increase,
Yes.
okay? A has to increase, right?
Yes.
So your, okay, so your, uh, this, um, your sum of, okay, the square of distances, right, is going to be the error,
Mhm.
right? Okay, and now you have to calculate what is called the slope of each of these. Okay, okay. So we say PC. Okay, principal component. Okay, so this line that you see, orange line or green line, we are looking for a candidate for PC, principal component. The one which has the lowest value is going to be your PC.
Yes.
Now, so now you have to calculate the slope of this. The slope is delta y by delta x, right?
Yes.
So this is your 90-degree, right? Now, okay. So now if you calculate, and when you calculate delta, you have to draw a line like this here, right? Now, your slope, okay, on, okay, each of this value is going to be, okay, so delta x by delta y. Now, if you have to calculate, let's say this line, okay, so this is, let's say, your, when you draw a perpendicular line like this, okay, this is your delta x, this is the delta y, correct? This is delta y change, and this is your delta x, right? Now, if we know x and y, that is slope, we can find this hypotenuse, right? Now, let's say if this delta y is um, uh, 2 and this delta x is 3. So slope is 2 by 3. We find slope 2 by 3. So if slope is 2 by 3, then what will be this distance? Which is 2 square plus 3 square, right? 2 square. So 4 plus 9, 13. And root of 13 is the distance of this, right? When we draw a perpendicular. So if I draw a perpendicular from here, okay, this distance is your change in y minus change in x, okay? So that becomes your, okay? So now in this case, when you have two different set of values, okay, you will have probably, let me take you back, okay, step by step explanation. Okay, so this is the best fit line. Okay, so this is, we are trying to minimize B, right? Keeping this as rectangle, and C is the distance between origin and the point, which will remain constant. This is what we discussed. Okay, and okay, if B decreases, okay, we see that if B decreases, which is B, okay, if B decreases, then to keep the value of C unchanged, we have to increase the value of A, right?
Yes.
Okay, so so finally you will end up having 6 A's. This distance you will have for each of the values, right? A, B, C, and we have D, E, F, right? So 6 values. So let's say, you got, so this is the error. Sum of square distances is A square plus B square, okay, plus 6 square, A6 square. So um, for each of the point, okay. So when we sum up the square distances from the projected points to origin, we repeat the process until we end up with a line with the largest sum of the square distances. Because if B is minimum, A will be highest. Okay, the best fit line that we end up creating using this technique is called PC1, principal component 1. Okay, now this is 1. Now to calculate the slope, the distance on y by distance on x, okay, so it will be, let's say 1 by 4. Just say it is 1 by 4. Okay, let's say it is 1 by 4. Okay, in our example, we got 2 by 3. Like in this example, let's say it is 1 by 4. In other words, what happens? 4 units that go out with maths. Okay, now which is on y-axis? What is on x-axis? Y-axis is your, again, let me take you to paint here better. Oh, we were in paint only, is it?
Yes, yes.
Oh, I didn't share. I wanted to share this one, sorry. Okay, you found the best fit line, and then, okay, so this is your C, B, A, right? And we are minimizing A. If you minimize A, sorry, minimize B, your A will increase. So finally your, okay, your sum of square distances is going to be A, which is A square plus B square for all the 6 values. Now coming to our PCA, okay. So this was what I said, slope is your
Distance on Y.
distance on y by distance on x, right? So if I go back to this, okay, in our case it is, let's say 2 by 3. Okay, slope of the best fit line is 2 by 3. Now 2 is, this is your, we call it as science mark. So yeah, y.
Yeah,
And this
science.
is your maths mark, right? Now what it says is, okay, it says for, this is 3x. So if you increase marks by 3 points, your science will increase by 2 points.
2 points.
Okay. If you are increasing maths by 6, your science will increase by 4. See, it is 2 by 3 and there's no negative, right? Negative means it is positively impacting. That's why you see the line is going up. Okay. It's a positive relation. So if you increase math, science will also increase. No? Right? Now, this is what we call as relationship between x and y. Okay. And okay, you see here it is 2 by 3 is almost same in the sense, 3:2 is what we are getting. Okay. Now to calculate the variation, okay, we, okay, so I mean, what you just saw is called principal component 1. Now, similarly, okay, we have to draw principal component 2. Okay, we have to draw principal component 2. Now, principal component 2, PC2, is opposite of PC1. Is opposite of PC1. Opposite means when you draw a line in quadrant 1 to 3 here, your PC2 is going to be 90° away from here. So you'll end up getting a line like this. Okay. And then again, you calculate, this will be 90°. Okay. So if you find your PC1, PC2 is always 90° away from PC1. In third dimension, you'll have one more dimension, right? So 90° in the third dimension. If you have fourth dimension, the 90° in the fourth dimension. Okay. So you'll have multiple such values. Okay. Now we calculate what is called as variation. Okay. So variation for PC1 and variation for PC2. Okay. And variation for PC1 is sum of the square distances, that is a square plus b square that we calculated, divided by n minus 1. So if you have 6 values, we divide by 5. Similarly, you calculate for PC2. Okay. Now, in our case, let's go back and check what is happening. Okay. So, yes, the next page. Okay. So, in this case, we got PC1. Okay. So, you got 1 by 4.
1 by 4.
Right. So, 1 by 4 is, see, 4.12 is the hypotenuse, right?
Yes.
And slope we got as
1.
1 by 4, right? So 1 is for y is 1 by 4, right? So like in our case, we got 2 by 3. 2 is for y-axis, which is science
2 is for
marks,
y-axis.
right? And you take the 13, root 13. So 2 by root 13 is PC1 for y-axis.
Y-axis.
And 3 by
3 by
root 13, okay, is PC for maths, x-axis, right? So you will get PC1 value of maths equal to, okay. In this case, it is 0.97 and science is 242. Okay. So this is your PC1 value for maths and science. Obviously, the one that will have higher, okay, will have a higher PC value, right? In our case also, if you say 2 by 3, maths will have higher value. Okay. So what it says is, yeah, 1 unit of vector along the best fit line we calculated, because best fit line will give you the denominator, right? Consisting of 0.97 parts of maths and 0.242 part of science axis. Now you see, if you add them together, you will get 1, because denominator is same, right? Root 4.2, denominator is same. So you will get, okay, so this is called SVD or eigenvector for PC1. Eigenvector. Okay. Okay. Now we have to create another parallel PC2. Okay. Now in PC2, you see, okay. Now here, okay, this is in opposite 90°, right? So here your x value, see, we were in first quadrant. In first quadrant, x and y both are positive.
Yes.
But in second quadrant, what happens? X becomes minus and y becomes positive. So you swap the values here. So maths will take science value, okay, because it's you're changing 90°, right? So 90°, this is what you will get. Okay, minus 0.42. 2.24. 24 is coming from the science part here. And then I can create, in third dimension also, this is how the values will change. So here maths is changing, maths becomes -1 and science become 4.
4.
So this is what you get. So this is your PC2 value for maths and science in opposite quadrant. Now, what is important for us is PC1 value. Okay. So now if you draw, okay, so let's see this here. Okay. To draw a final PCA plot, we need to draw a final PCA plot. We rotate everything so that PC1 becomes the horizontal axis. Okay. Now your PC1 becomes horizontal axis. That means you have to bring it down, right? You have to move it down to orange, this x-axis,
X-axis.
right? So you have to move red to onto this, blue, and this dotted blue onto this y-axis. Now your points will also change, right? Obviously, right? So the first step was to move it along origin, and second step here is move it to the axis.
Mm.
Okay. So your total distance variation will become this. Okay. So squared distances for PC1 by n minus 1 is a variation for PC1. Okay. This is how much you have to move. Okay. Now you assume the variation of PC1 equal to 15 and variation of PC2 equal to 3. This is assumption, right? So total variation across PCs is 18. Okay. So PC1 accounts for 15 by 18 and PC2 accounts for 3 by 18. So you'll have 83% and 17%. 83% and 18%. So, okay. So this is like contribution made by your PC1 and PC2. Now here PC1 and PC2 contribution is 17% is also significant, right? So probably you can keep, you can keep it. Now when you create a three-dimensional, okay, you might get something like this. Third, okay, contribution maybe 3% or 2%. So you can decide to keep first two feature and remove the three feature. Okay. So yeah, understanding is little complex. Okay. If you follow this, you will get it. But anyway, this is for your understanding. What we are doing here is we are trying to find the principal components. And how many principal components we'll have will be same as number of features in starting. In starting, if you have three features, you'll end up getting three PCAs, right? And we need to decide later, okay, which PCs we need to keep. Now, first line what we drew, PC1, okay, that will be for,
X-axis.
right? And then let's say if you have third axis, this is what we get,
Yes.
okay? So in this case, English is most important for PC1 because English
Yes.
is 77%.
Mm.
Okay, now if you have a PC2, right? And we have to draw PC3 as well. Okay, third this thing, axis, third dimension. So for PC2, maths is more important.
Mm.
And when you draw, okay, PC3, okay, so you'll say that PC1 is 79%. Again, you calculated the way we calculate 2, you calculate for 3. So which says that PC3 is least important here. Okay,
PC3 is
if
third quadrant, right?
third quadrant, yes. So you'll draw another 90 degree on the third
Yeah.
axis,
Mm.
third dimension. Okay, and everything will move now there. So ultimately, okay, so it is very difficult to visualize 4 or 5 dimensions, but our program will be able to do it for us. So it says PC1 is 79%. So PC1 probably you will take, PC1, PC2 you will take, PC3 can decide to drop. Even if you drop PC3, your actual will be impacted by just 6%. So sometimes, it's like sometimes you might lose accuracy, but the loss in accuracy is very insignificant, very less. Okay. But the benefit of doing PCI is high. Not always you lose. Sometimes, if it is something which is very less important, and if you remove it, your accuracy can also increase. So it's not that always you will lose accuracy. Okay. Most of the time you will gain accuracy. Okay. But good thing is, okay, when you gain accuracy and also you gain time. Okay, but even if you lose accuracy sometimes, okay, your the amount of time that you gain, efficiency that you have, is much more than the loss in your, and this is not done on 2 3 variables. When you have large number of variables, right, that's when it happens. So your last one will probably be contributing to 0.0001%. Okay, so simply you say extrain PCA dot fit transform. That's it. So okay, so it's going to give you your variances 57, 52. In fact, I did one on multiple this thing. Okay, so what I'll do is I'll share this example with you guys. Okay, I want you to practice this. Okay, so there is a data set, okay, called Sonar data set, and if you do Google, you will get this. Okay, this is very common data set. So it has 208 samples. Okay, that means rows. It has 60 columns. Okay, it has 60 columns. Now, so it has, based on various characteristics, you need to predict whether it is a rock or a mine. Okay, so based on the characteristics, the sonar will classify whether it has hit a rock or a mine. Okay, so this is the uh, you know exploited data science. You can see how many mines, how many rock. This is a histogram for each of the attribute, each of the 60 attribute. Okay, this is PCA. Now it has given us, okay, values for all the 60 columns, PC component. Okay, so C starts with -1 means 0.0, right? So it is 0.33, 10 to the power -1, right? So it is 0.33. The first one is 0.33, 0.20, right? Now if you go to the last one, you see 2.7, 10 to the power of -6. That means 0.5 times 0, 0.000026. So probably, you can delete this. So what we have figured out is two attributes itself can explain 54% of the data, 0.3 and 0.2, right? So 0.3% and 0.2, that is like 33 and 24. So if you take these two together itself, 54% of data. Okay. Now if you take 11, these is totaling up to, okay, is it 11? 1, 2, 3, 4. 4 plus 4. Okay, no, this is yellow part. Yellow part is your 11. So 11 alone can explain to 90% of the data. Okay, 18 alone can explain 95% of the data. So imagine, okay, so you don't have to worry about all the 60. Okay, so and you also know that, okay, the column which is giving you this is probably, you can ignore, right? You can ignore or 10 to the power -6 kind of thing. So this is what PCA will tell you, which columns to include, which columns to exclude. Okay, and then you can run, different model here. Okay, so I'll give you this also. So again, please practice through this. Okay, and this is just this thing. What do you call it? The notes, but here I have the code as well. Assignment with code. Can you see the code? Right? Yeah. This is your. Okay. Okay. So accuracy is 75% here. This is the entire code. Okay, I think sonar data is there in my this thing, or you can download it also. Okay, it's there available. You can download and practice this. All right. So try this. So with that, okay, we complete our classification example also.